So this is a regular bi-weekly meeting, and we mostly focus on low-level performance and everything that is related to that. So, like how to analyze and find performance bottlenecks in your application. We talk about hardware, operating systems, compilers, high-performance libraries, programming models, and so on and so forth. And then, so performance is a huge topic, right? And it's very complicated. Well, but that's great. So we have people with different backgrounds. So that's always nice to have. And so today we have Daniel. Daniel Lemire or Lemire. Daniel, how should I pronounce it?
Well, because I'm French speaking, it's Lemire.
Lemire, okay, yeah, thanks. So Daniel Lemire is a computer science professor at the University of Quebec. He's a contributor to major open source projects and a long-time blogger. And also Daniel is one of the most popular GitHub developers. So Daniel is the man behind such projects like SimD.json, Roaring Bitmaps, FastFloat. Daniel, welcome. I'm really excited to have you. And I'm sure I didn't mention many of your other accomplishments, right?
Well, no, but that was a pretty good introduction. Thank you.
Yeah, sure. So Daniel, let me start with saying that I'm glad that we have such a strong player like you that also has a huge academic background, right? So tell me please, is this low level performance? Is it a hot topic in academia?
No,
no.
It's a freezing topic. So that's a very interesting remark. So there are relatively few people on campus, and I don't mean none, but I mean relatively few that are really interested in software performance in the way that both of us understand it, right? So I'm a reviewer for for many academic conferences, and I'm even an editor of a journal that's called Software Practice and Experience, and even in the journal. The major reason why we reject papers is because they're unrelated to the software practice and experience. So actually, academics at large are a lot more concerned with what I would call algorithmics. So I would say that hardware independent ideas are much more popular. Something like mechanical sympathy that is the in that. So if you read someone like Newt, for example, who has this a very, very thick book that he wrote over 2 years, the way he works is that he's basically he has actually formalized an assembly language, and but you see that the way it works, right, is that he's thinking of a machine, maybe not the machine that you have on your desk right now, but he's thinking about an actual real machine, and then he's trying to model the performance in terms of that, and so he provides these results. Now, what's happening a lot of times in academia is that there's actually no machine at all in the mind of the people. So they like to work, and I'm not talking about everyone. I'm describing, a sizable fraction of the community where they basically think about models. So they prefer to work with models. So there's a fellow named Jeffrey Allman who won the Turing Award this year, and so he's a little bit infamous because he made comments that are controversial about Iranians. But and basically, if you go to his website, he's got an essay that's basically. Basically, he submitted this paper to a systems conference or some people doing cloud computing, and his paper got rejected because all he was doing is doing big O analysis, and he said, well, you should validate your findings using experiments. And so he wrote this essay where he actually takes me as an adversary, and he says, well, look at these stupid people who think that you know that basically big O notation is not the core. It's not of core importance when you're designing systems, And so he's basically saying, well, we should probably not focus too much on experiments because experiments are, they can be wrong and so forth. And I think a big concern in the academic community is that they want to. They often want to do work that is independent of the hardware on the premise that the hardware is going to change tomorrow or in 2 years, right? So I once gave this talk where I was focusing on what you could do with today's computers, and if you narrow it down to say 64-bit Intel processors, you have all these neat things that you can do. And someone came to me afterward. He said, well, but what are you going to do with all this work when 64-bit Intel platforms are obsolete? And I said, well, okay, but hopefully I'll live long enough that I'll still be working, and then I'll work for on whatever platform there is then. But I think that this actually pretty much illustrates the frame of mind of not everyone, but a lot of people, where they actually do not want to take into account the whole stack. They want to work with models of what performance might be.
Right. Yeah, that's a great point. And yeah, and we have a few other let's say involved people from academia, like for example Emery Berger and John Reger, right? So those two are also very very famous and popular. And then actually, so speaking about this knowledge, about this low level performance knowledge, so my perception is that there is a certain amount of performance ninjas in the industry, right? And those folks sort of keep this knowledge and well, of course occasionally sharing, but still this knowledge is scattered, not consolidated, right? So do you think that performance should be approached in a more systematic way, maybe starting from academia?
Well, okay. Well, first, this point that you make is very true. So you wrote a book, right? And you pointed that out. And this book, which is great, doesn't have a lot. Well, it probably has some competition, but probably you surveyed the field before you wrote it. My expectation is that you don't have a lot of competitors, right?
That's true.
Right. So that's probably why you figured that it was worth your time, to invest that much energy into the book, because there's basically not a whole lot. So something similar. Well, not really similar, but something, a book that you probably know about, is Hacker's Delight, which is this kind of odd book that is a little bit of a classic because it describes, but these books are fairly uncommon, right? So they don't come along very often, and I don't know. Maybe there's a huge market for it. Hopefully there is for you because you wrote the book. But it's true that this knowledge is all over. So last year I was at a conference, and they asked me, where should I go to learn about software performance? And though I can cite your book, essentially the answer ends up being kind of fuzzy, because it's to get to know people who are good at it and work with them. Now, you pointed out that it could start from academics. Now, one problem with universities is that most college professors don't build software, right? They don't. That's not what they do, right? So if you go to a music academy, the professors there are probably pretty good music players. But if you go to an average computer science department, the average professor is probably not a great hacker. Because I'm a professor, I know what they do, and so they write papers, they apply for grants, and they supervise graduate students, and they try to get papers written, and sometimes they give a lecture and that kind of stuff, and so they don't have a lot of time for programming. And there's a presentation by Knuth, it's probably somewhere on YouTube, where he kind of makes fun of that, because he says, well, okay, so I'm going to present my latest work, and I've basically outsourced all the programming to other people. Because as you know, like he actually, well, he's not writing a lot of software, but he actually wrote the software for tech, which he used to write his book in. So these kind of people are kind of uncommon. So that's a difficult take. Even if you go into software engineering, probably these professors don't write a lot of software, and they certainly very often they don't write it with performance in mind at all. So it's difficult to start from there. But I think we could definitely do more to organize it. But I'm skeptical of doing it without the input of, say, people like you. It's probably not going to work. So your book was a great step in this direction, and I think it's probably the way it should go. So it could be, it could be like there are some conferences. So it could be that's good too. So there's a Facebook. People at Facebook organize like a performance summit. So that's pretty good. So these things are certainly helping. And the event you're organizing right now, Twitter Spaces, is great. And all of these things, I think, are probably very, very useful. I don't know if it answers your question, but I'm just skeptical. Yeah. And it goes back to I think it's Paul Graham, who has an essay who's basically saying that there's a problem with colleges because they're not teaching programming, they're teaching computer science, and there's a big difference.
Right. That makes sense. Yeah, that makes perfect sense. Yeah. Yeah, that's interesting. So Daniel, let me maybe ask then. So, what motivates your work? So, so you obviously started many open source great projects like SimDJs and Roaring Bitmaps, Fastfloat. So, what was the trigger for you to start those projects?
So I learned to program in a long time ago, so I'm old. So I learned to program in the 1980s, and at the time I would I would write code, and I would at the time there was no internet, so you either bought a game at the store or you made your own game. And so I would, for fun, just program games. So I was a kid, and so I programmed my games. And very quickly, what I found out was that I was constantly limited by performance. I was writing code in BASIC and trying to display things on the screen. And it got really, really frustrating because I could not I could not achieve what I wanted. And then I would and it went on and on and on for many years, where I would. So I remember one project I did was with geophysicists a long time ago, and these people were collecting data, and they said, "Can you come up with an algorithm to correct our data, to baseline correct it?" And so I did, except that I tested my data on small samples, and then they say, "Okay, here's the data." And so they gave me these CD-ROMs at the time, which had hundreds of megabytes of data on them, and then my little puny algorithm, was taking hours. And then I realized something was terrible, because if I wanted to adjust the algorithm and see how well it did, then I had to wait, hours to see how well it was doing, and that was no fun. And and so I was really I'd taken to heart what I was told, that focus on having clean code and don't worry about performance, and it's all going to work out. And so I would write these I would write code that was pretty and well documented, but very often was it ended up being a little bit over engineering object-oriented monsters to a point, and I think I got really sick of it when I was doing some project where I had to load a lot of CSV data, so comma separated value files, and was incredibly slow. And I was spending half my time waiting for the damn things to load in memory. And then I started looking at the code that these people were using. And then I realized that the code was multi-threaded. And it was slow, but even so, it was multi-threaded. And so I think at some point I saw the light, and I decided maybe we ought to stop doing that. We should we should stop writing huge piles of pretty code, and then trying to and having to pain and trying to change our approach entirely, that to go for readable bug-free code, but also focus on code that is lean and fast, and that it's not true that you need to compromise everything. Actually, you can achieve all of it. You can have code that is pretty lean, flexible, but it's also very fast. So that's I came to it slowly, but like a lot of people, I was processing data and having to wait a long time and being constantly frustrated. And then I learned that it was another way, and I guess as you're saying, one of the reason why it took me a long time is that this precious little exposure to high performance programming early on. So when you teach programming, and I do teach programming, it's simply not in the cards, because the students can barely write a for loop that works, and so you don't worry about it. And then even later, it's difficult, because there's so much to learn before you can focus on performance, that it takes a really long time. And so maybe a lot of programmers, I think, end up skipping that point. So they learn to program well enough that their code works, but then they never get to the point where they focus on performance. They just skip that, and then they go write software for a living or something.
All right. But so then how you started, for example, CMD JSON or fastFlow. So like what was the trigger, right? So for you to start those.
Right. Okay. So so
how you found the idea? Yeah.
Yes, I understand the question. So let me okay. So So if you look at many of the projects that I've worked on, you'll find that a lot of times it has to do. I mean, so I have this saying that programming is social. So if you look at many of the projects that I've started, a lot of them came about because I met people, or I started exchanging with people. So sometimes it's someone who says, well, I've got this problem. This thing is terribly slow, and maybe we should be able to do better. So in the case of JSON, for example, this is how it came about. It's basically I was reading this blog post, and this person was looking at benchmarks, and this person was observing that actually the bulk of the time was spent on JSON, loading JSON. And if you were listening earlier, you know that I had this problem earlier in my life where I was trying to load CSV files and they were really, really slow. Mm-hmm. So I looked at it and I realized that this person was entirely right. So then I turn around and I say, okay, who can help me make this go fast? So I found Jeff, the original co-author, and he said, yeah, I think we can go much faster. And all of the projects have to do with these social encounters where you basically, there are first people who express a need, they document a need, and then being able to find the right expertise, the right people around me who have either the idea or the low level knowledge to make it work. So a lot of times that's how it comes about, and this goes into I think an important point is how do you make really good code and really efficient code. And my own approach, and I didn't invent that at all, but very often the mechanism that works really well, I find, is that you have this partner. So let's say the two of us, so I've got this problem, right? I need to write this function that does something. And then I want to make it go fast. So what I might do is I'll write my code and then I'll share it with you. And I'll say, well, you're pretty smart and you've worked on similar problems. Can you make this go faster? And then maybe you look at it and then you come up with these ideas, right? And then you'll send it back and you'll tell me, well, I made it 2 times faster. And then I'll look at your solution and say, oh, but I can make it 2 times faster even, and so forth. And then you get this iterating process, whereas each time the other fellow looks at it, they can improve the performance further and eventually converge to something that you can sort of prove cannot be much improved. And that's a great process, but it's a very social process. One project we worked on was Unicode UTF-8 validation. So, and I started very, very naively on my blog saying, okay, so you've got all these Unicode strings out there, and before we put them into our database or so forth, or parse them, we should validate that they're actually valid. Otherwise, it's a security issue and so forth. And then I said, okay, let's see. And then I did something that was, I showed, okay, we can probably do something that's better than what most people use. And so I made this demo. And then other people came along and had ideas. And we had this iteration over the internet. It was open until basically we wrote a paper last year with a solution that will sound entirely crazy to anyone reading it because it sounds like it comes out of nowhere, but it's very ingenious. But it combines different ideas from a lot of people over time, and so I think that summarizes a little bit of our work. So the motivation is really found into hopefully practical application. So I like to listen a lot to actual engineers who have actual problems who actually have data that they need to process quickly. So that's a very important source. I think as an academic, I don't have these problems per se. So for me, it's very precious to listen to people who who do real work for a living instead of just academic work. And then if you just listen to these people and the problems that they really have, then I think it's possible to come up with projects that will, if successful, interest them again. And here I go back to I think academics are sometimes too disconnected. So there was a talk by Stonebreaker, the fellow who's behind a lot of very important database work. And he gave this talk where he says that one problem with academics is that they no longer have customers. That is, they give these talks, but nobody listens to them because nobody outside of academia, because nobody cares about it because they're not working on the problems that matter to people who build systems. And so I try very hard to avoid that.
Yeah, that's true. Yeah, and your projects, for example, like SIMD-JSON is very popular, right? So it's used in a major by major software vendors, right? So that's a great result.
Well, but even if nobody ever uses the software, very often it's not like to in my case, because I don't make a living with the software per se, it's not necessary that people use it. All that's needed is that because for me, and for everyone, including you, but it's really more for me maybe than other people. Software is a way to communicate ideas, right? So even if you work in a team, so you say you work on compilers, sometimes you'll write code, right? You might write code to explain an idea, and it doesn't really matter probably to you whether this code actually ends up in production. If someone says, okay, that's a good idea, let's implement this properly, and they throw away your code and they start working on the idea that you conveyed, then that's good enough, right? You don't, right? So that's the idea. So even if I write a project and nobody uses the code, that's fine, as long as I can make it so that they use the idea. Then that's really the important thing, because then we move forward. But of course, it so happens that it's correlated, right? If people use your idea, they're more likely to use your code also. So it's a measure of whether it's happening. But I'm totally happy when people take my a piece of a project that illustrates an idea, and they say, well, but we're not going to use your code, we're going to re-implement it. And I say, okay, that's fine, good. I'm super happy, even happier sometimes. Yes.
Yeah. So like, if the idea is great, then we can always iterate and reiterate on this idea and make it better. Yeah.
Right, and what's really powerful is when people take your idea, they look at your code and they re-implement it differently, and they get again good results. Then it's validation, right? So it's a form of experiment. It's an independent peer review. They actually validate that yes, your idea was good. Or they find out that it was bad, because could happen that you missed something, and then when they re-implement it, then it doesn't work. But then that would be very informative too.
Yeah, that's great. So Daniel, let me switch gears for a little bit. So how do you approach performance engineering, and how do you find performance bottlenecks? So like and in particular, how do you find opportunities for improving performance? Let's say you have some application at hand. Let's say, for example, you for example took a look at these other JSON libraries that are out there, and you said like, hey, we can do better here. So how what's your approach to finding the opportunities for improvement in with regards to performance?
Okay, so one approach that so performance actually. So one of the reasons earlier why I was a little bit mocking the idea that you should just write nice code and then worry later about performance is that performance is actually it's like correctness. It's a first principle. It's something that should be on your mind from the get go. Because then if you don't have to write architecture, then that it doesn't work. Sometimes it's impossible to recover. So one thing that I don't tend to do, and I understand why people have to work this way sometimes, but one thing that I very rarely do is take code and then profile it and then find the bottlenecks. I know this is standard, but it's uncommon that I will do that. Rather, what I do is I try to make cost models in my mind. So I say, okay, so for this task here, what might be a reasonable budget? How fast should we be able to do that? And then you try to have different approaches, and you try to I tried to compute it in my head. How good could this be? And then after that, I run a lot of experiments and benchmarks. But benchmarks, as long as they're well designed, it doesn't matter too much whether you've got a lot of fancy tools around it. If you've got the numbers, then I compare against my estimates, and then I figure out, well, okay, so I'm at that level. So then I conclude that it might be possibly a large improvement, or else I conclude that this is probably good enough. So that's very often I work. I try really hard to also to measure constantly. I measured the first solution, and I think it's probably discussing in this kind of approach is probably discussing in book. I don't remember, it's too long ago, but basically I measure at every step. So for example, in SimD.json, we had this system where it's still running. I think with every commit we would have a plot that would update itself with the performance numbers, and so we knew the effect of each little change that we were making, and I think that's something people don't benchmark enough. I think that's a very big problem. Back in the 1980s, nobody would run unit tests. In fact, people did not know what unit tests were. In fact, people did not run tests at all. So they would just say, "Oh, it works on my machine," and then nobody does that anymore, right? So if you're working on the compiler, you're not going to say, "Well, I tried compiling, a few programs and it works on my machine, so let's ship it to the customers." It doesn't matter who you are. Nobody does that anymore, right? But we do that constantly. We do the equivalent constantly with performance. We just
right. Yeah, that makes sense. Yeah, that makes sense. And actually, so one remark I want to add is that sometimes people ask me like hey, so so how we can start improving the performance of our application. And my answer is usually is that just write a benchmark for it first, right? Because what's managed gets what's measured gets managed, right? And
you're absolutely right. So what gets measured tends to get improved. So
yeah.
So if you're not measuring it, you're probably not improving it. But the whole idea with so to come back to your original point, how do you find bottlenecks? So I don't know your experience, but I've found that of course you want to we all know that programs spend 80% of their time on 20% of the code or something like that, right? It's kind of obvious. I find that doing the profiling work and then finding out which lines of code are hot or something, and then working from there, I really get some. It's not. I don't find it very fruitful. To me, it doesn't really help very much, and I don't tend to recommend this approach too much. I think it's better to think, okay, to reason a little bit about the problem, and very often I would urge people to start reasoning from the data structure. So you look at how your data is laid out, right, and you look at what do you want to achieve, and then you try to map the two, and then try to find the most efficient approach, and that's usually a much more fruitful way to express the problem. Because if you're just trying to profile it and find this line that uses a lot of time, you'll then be stuck staring at the line and trying to write it in different ways, and it's probably not going to help you a lot. But then of course, if some idiot wrote the code before you and he's using insertion sort on gigantic arrays or something, then yeah, you'll spot it with profiling. But I guess the point is that then if you're working with so it might be different in a context where you're working with code that was written by idiots and you're trying to improve it. But at that point, you probably have big architecture issues too that are going to hurt you, and so you might want to start by redesigning the application rather than trying to narrow it down to finding the stupid lines. Yeah.
Yeah, that makes sense. And I actually like your the point that you make, that asking this question, like how good can the solution be? That's and the thing that performance can also be approached from the first principles. This is actually a very good remark, that so that so that you start from the let's say from the theoretical maximums of your machine that you're targeting, right? And then you figure out, like, so you have this roof line, right, that you cannot that you cannot overperform, right? So but at the same time you try to get your performance to the level closer to the theoretical maximums of your machine. So that's a great point.
So the part of my training was in physics, right? So and I shared that feature with Elon Musk. Now, whatever you think about Elon Musk, you might think he's an idiot, but the way he explains problems sometimes, where he starts from first principle, right? He says, okay, so to do something like that, here's how much it would cost, and here's how much energy I've got, and so here's the range of possibilities, and we're there, so we're too fat, so we can get much leaner if we do this. I think that's the right approach. I don't actually know Elon Musk, so I don't know whether he actually applies this approach. But the way he talks sometimes about it is actually the way I think people should talk about software. To me, making software efficient is not very different from like making an engine efficient, right? So cars are about 2.5 times more fuel efficient. Actually, it's more than that. It's probably 3 or 4 times more fuel efficient than they were in the 1970s, right? And the way this comes about is just basically sound engineering in physics. You start, okay, we can make the car lighter, the pieces smaller. There's the oil there, and we can use better oil to reduce the friction. And then it's all these first principle reasoning. One of the reasons why I don't like the profiling thing is that it can turn into a headbanger. where you're just randomly trying things, and and you're not sitting down to think it through from first principles. So you're just stuck, you know. So I think it's better to you benchmark. You try to understand your numbers. So you benchmark your code. Then you try to, basically it's a scientific approach. So you got this model in your head when you start out. You benchmark. Now you compare your model with your model in your head. And if they disagree, then you update your model until it fits the data, and you run a lot of benchmarks until your model it sounds good. And then from your model, you can try to say, okay, what can I optimize? And then you're going to get, then you might get some really, really powerful results. But if you're just, finding hot code and trying to tweak it more or less randomly without mechanical sympathy, without knowing what's happening, then you're probably just going to try random things and it's going to work. But, well, first you're going to hate it. It's not very productive work, and you're probably, it's likely that someone will come after you and then will show you how to make your code 4 times faster, and then you look like an idiot who spent a week trying to optimize this code, and someone just made the function disappear and redesigned the code, and you just wiped away your work. Which reminds me, one idea that we could do to actually make software performance more accessible and more fun would be to have these. Someone should organize competitions. Where you of course you need to set the rules because people can cheat, but where you try to have code that's as efficient as possible given a problem. And you were mentioning John Rigger previously, and I think he did that in his class at least once, where he set up this problem. He says, okay, who can come up with the most efficient solution? And I think that's something that we should be doing. And I'm going to be teaching advanced programming starting next year, and in that class, that's what I plan to do. I plan to have a competition of sort, where not necessarily against the other students, but the idea is you say, okay, here's a problem. Can you come up with an efficient solution? And then once the student is finished, say, okay, well, here's a solution that might be more efficient than yours, and then maybe you grade accordingly to how close the student came to the really, really efficient solution. And that's a very good spirit, and it's actually nothing new, by the way, right? Because as I was saying earlier, if you read Knuth, that's more or less how he thinks. He has he actually spelled out an assembly language of his own, and then he actually counts instructions. You can see it in his books, so he doesn't write in C, but it's the same idea, right?
All right. Yeah, that's great. Yeah. So actually, speaking of optimization opportunities, so where do you think in the technology stack where we have the biggest opportunities for performance improvements? Is it hardware? Is it operating systems? Is it libraries? Or the major part of the optimization and performance tuning will come from the and should come from the application itself?
Yeah, that's a very good question. Well, first, I always like to put these things into context, right? So, as I was saying earlier, cars got a lot more efficient, but it's true for every industry, right? So, the Green Revolution made agriculture, again, something like 3 times more efficient per unit of land. In computing, our story is ever more optimistic, right? Because I did not actually even try to measure it, but since the 70s, we're probably like 1,000 times or even more efficient. So we're in a great industry where things are going up all the time. There's this sometimes common belief that hardware does all the heavy lifting. So you work for Intel, so maybe could be a popular belief there. But anyone who actually knows what's happening knows that it's more of a co-evolution, right? So really cool software without the hardware or vice versa is not great. So so the two work hand in hand. So for example, if you look at the Chrome V8, the V8, the JavaScript engine is an example that I like to cite. I don't have the latest numbers, but between 2008 and 2018, according to their blog, their performance went up by a factor of 4. And that's despite the fact that V8 is much more featureful now than it was when it started out. Right? They do a lot more, so it's a lot fatter, but they still go 4 times faster, and that's a 15% boost of performance per year. So it's about, I don't know the exact number, but it's not a lot more than what Intel did, for example, with its CPUs, right? So we do not see like a 2x factor per year from Intel. So this is really, really important. We have this we have this efficiency that keeps on rising, and one of the problems that we have is that so for hardware that's fairly easy and somewhat predictable. For software, so you're talking about, is it the operating system, is it like the applications? One problem that we have very often is how do innovators capture the benefits of the speed boost, right? So if you're Apple, for example, and you're optimizing iOS, then it's really easy to see that you're reaping the you might reap the benefits, right? So there's apparently a new very nifty scheduler on macOS that's really giving the illusion that things are really, really smooth, and it's really helping a lot. But then Apple is this large company that can reap the benefits. It's a lot harder for the independent developer who comes up with this neat approach to actually justify spending a lot of time on software performance issue. One area where I'm very hopeful is probably open source, where we see a lot of projects where there's really because basically a lot of our software infrastructure is open source these days. So there's a lot of work there, and a lot of projects that have benefited greatly from really neat performance enhancement, and they come from all over the place, right? So, Intel will contribute, but so will Amazon and other people, and that has we've seen in some cases some amazing work that has led to really good work, and open source is, to me, the way I view the software community is part of what I call an invisible cause, right? So it's the idea, it's part of all of the things that you were saying, that the knowledge was diffused, and that's part of it is that basically if you're not part of the college of the good actors, then you don't understand where the performance is at. But if you're part of the college, if it's an invisible college, you don't see it. But if you're part of it, then you start knowing, right? You start to know how it happens, and open source is part of it. So recently I worked with the students on a port. So our fast float. So we found out that we could parse floating numbers fast, and I was working with a student. And I said, well, why don't you port the code to C# and see what happens? And I'm not an expert in C#, unfortunately, but what was very interesting is that I was able to predict to the student, okay, here's how it's going to work, right? And here's how the people are going to think, right? And it pretty much happened how I thought it would. And just basically because it's a community, and we understand, like I've never worked with you, but I probably would not be surprised by how you optimize software, because we have all this knowledge, but this knowledge is kind of shared. And one way to one aspect that really benefits from it is open source software. So the stack really benefits. Now, where will performance come from? Well, basically it depends on your scale. So as I was trying to put it in context, we see these efficiency benefits in every industry, and computing is no different. And typically, the way it works at a high level is that you've got these transformations that come along, right? So there's some new idea, and then people milk it, and when they milk it, you've got this exponential curve where they derive a lot of benefit, and eventually they're done milking it, and it stalls, and basically the benefits they've spread. So all of the software matters uses this idea anymore. There's no more benefits. And this effect will come everywhere. So it will apply to the hardware all the way to the application level, for sure. So I think it's really hard to predict where it will happen. But as I was saying, my guess is that a lot of either infrastructure software that is owned by large corporations that can really reap the benefits of their optimizations. That's one angle, and the other is probably open source, because it's infrastructure, but it's infrastructure that everyone can benefit from, right? So it's a good target to optimize the code, because then even though you don't benefit, your invisible college will benefit, and so it lifts all boats, and so people are motivated to do it. But if I'm writing an application for the iPhone, then I don't know. Like, I'm not sure the practices regarding performance are going to change drastically. I don't know that if I were to write an application, I'd be super focused on performance right now. That would not be my priority, right? So I hope that people who built the stack that I'm using I've really worked hard on performance.
Yeah, that's interesting. So and yet, Daniel, I know you like making predictions. So so it could be interesting to you. So actually, yeah, so one thing that I see that is that
but if I may intervene here,
sure.
So yeah, I like to make a prediction, and actually, it's actually fairly easy to predict these things, because this is a very good point, because actually it all follows the same curve, right? Like Moore's law is the obvious example, but really people say Moore's law is falling, but you can really see it continuing if you just care about performance, right? It's not true that chip makers are sitting on their hands. They're making things go better, and everything is tends to be on very predictable slopes. So about 10 years ago, I predicted that my iPhone in 2020 would have 1 terabyte of storage, and people thought that this was an insane thing to say back then. And of course, my iPhone does not have a terabyte of storage, but you can buy an iPhone with half of that. And all I did at the time, well, it wasn't really a prediction. I just plotted the curve and I just extrapolated, with an exponential. And the exponential tends to work out in these cases. And we see, for example, disk performance and network performance. They're actually fairly easy to plot, and they follow really, really smooth curve if you follow along. And JavaScript, for example, performance follows a nice exponential curve too. And it's probably before it level off. There's probably many years to go too, because there's still a lot of fat.
That's interesting. Yeah, and then also people come with all sorts of different accelerators for
yes.
for the streamlined hardware that is dedicated for a particular workload. So they can build a really nice hardware that is sort of know how to solve a particular problem.
Yes, that's co-evolution, which is a really, really important feature, right? Is the idea that, well, okay, so Intel comes up with X-Point or something, right? Some new technology, but then if the software is not there, then it's worth it. So, but people come up with the software, and then it justifies more hardware and so forth. So you've got this co-evolution where we never run out of steam because there's literally an infinite domain that we can explore, and so we can always find more efficient ways to do things, and people don't tend to believe that until they've looked at the trends. It would have been unthinkable for someone in the 1950s to look at the productivity of our farms. And what is boring, right? You're talking about farms. How could it get so good? How could they multiply the output per unit of land? But it did, and that's because there's basically this infinite domain of innovation that you can tap on. And I think software is the primary example of that, because we're way more than 2.5, but it's very predictable. We can actually, if you look at different trends, you can really extrapolate, and you can be very, very. Every few years, there are people who are really pessimistic. They say, well, okay, software has reached the end, or performance has reached the end, and that's it. We're going to stall from now on, and so stop building software that has more functionality, because we're not going to have the performance. But of course, it's always wrong. It's always wrong. We always can do 10 times more because we have 10 times more efficiency over time.
That's interesting. Yeah, that's interesting. So Daniel, let's talk about tools, about performance tools. So, do you think we have actually a good enough tools, like from a? I mean, it's hard to look from the beginner's perspective, right? But if you would you say we have good enough tools for performance engineering, or you don't?
No, well, I think it's terrible. And starting even from the basics, like I was alluding to the fact that most projects these days have, it's pretty much standard to have unit tests or some kind of testing to see that as you go along, you're not introducing new bugs all the time. But I'm sure there are people who have, performance monitoring during development work that is comparable to that. But it's certainly not widespread. I certainly don't see it, right? And it's and there are very, very, very hard problems there because so for example, if you write code that can be compiled, using different compilers, then good luck figuring out what's happening, right? And there are lots of really, really simple problems that are very, very hard to. There's just no tool, to my knowledge. I mean, there probably are, but they're not widespread. That there's no tool to solve these problems. So one example that if you have this code base sometimes, and if you change, you can change a single line of code, and then you look at the assembly difference, and it could be like 5,000 instructions that change. No, maybe not that bad, but it could be like vastly different. Right? So you look at the assembly dump and it's completely different. It's really, really hard, but actually probably not all different, but just comparing, just understanding what changed, how did the compiler react to your one change, and can you understand the effect in a complex code base? We just don't have to my knowledge, not very good tools to do that. And so we got better at things like profiling, so you got these flame graphs that are kind of nifty, and that was progress in the slate. That it's silly, right? Because it looks like just a plot, but to me this was progress. I find the usability of the benchmarking frameworks sometimes quite poor, in the sense that they're not. One annoying thing that I find is that very often they run slowly. So benchmarking your code takes a long time, and the assumption is that it doesn't matter because you're not going to do it frequently, very often, and of course that's the source of the problem, because you should be constantly benchmarking. And so if it takes a lot of effort to benchmark, then you're not going to do it frequently, and I think that's part of the problem. And so we don't have these really, really quick, very convenient, very instantaneous benchmarks that happen all the time. There are other things that I think the community gets wrong that are like even first principle, even how to benchmark. I pointed out that maybe your book was one of the very, very few ones, and you do cover some of that. But like for example, there's relatively little discussions about the distributions of timings or stuff like that, which there's a commonly held view that the timings follow a normal curve, which if you plot it is very often not the case. So even basically simple statistical things can be wrong. And so I think there's a lot of room for progress there. A friend of mine was working on a super optimizer, and the idea, and there's a lot of work there to be done. So you have these very simple problems sometimes where you're looking at a very simple task, and say you're using 5 instructions, and that's what your compiler does, and you're wondering, well, could I find a function that does it in 3 instructions? Now, you would think that it would be possible to, say, well, I give this problem to my compiler, to my processor, and it has one day to work on it, and then it's going to give me back the answer, right? That would be a very neat tool to have, but we don't, to my knowledge, we don't have things like that. At least it's not common use. So you have all these people who, like me, who code crazy code routines that look really mysterious, but they come out of our minds, and they're often not they're not very they're basically pieces of act that work, but it would be really nice to have better tools to do them. So yeah, I'm fairly negative with respect to that. Now, what I think is amazing are the optimizing compilers. Like these things are really, really, really fantastic. I mean, people complain all the time that some people complain that they have to write assembly to get the most performance out of their code, but we've made great progress. Like if you take a 30-year perspective on the work that compiler do at all levels, they're much, 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 much incredibly better now. It's like amazing. So it's a lot easier to, in this respect, compiler as a tool is a much better engine. But yeah, we're missing a lot of things. We're missing really like to things like to explore assembly. Honestly, like a giant help was the online tool Godbolt, where you can share with other people, assembly. This was a brilliant innovation. It's really simple, but we're basically, and I tried working with a student, but these problems are really hard, on building tools that help people understand the assembly better. Because there you were talking about how you get, you say, younger people maybe, or people who are less experienced with performance to be better at it. One of the big problems we have is that we tell them, well, look at this assembly dump and figure it out. And this is ridiculous, right? These things are really, really hard to read, and there's a lot of information there that you don't actually need. Very often it doesn't really matter which register it's on. Who cares, right? And so you've got in your mind to abstract out all of this information and figure out what's happening. And we just don't have very good tools for these things. And I think someone should write them. But then we have the problem of how do we capture the value of that? Because these things require a lot of work. So Intel, for example, writes some good libraries and good compilers, so forth. But it's really hard to capture the value that such things produce, right? So that's why I think people are not so eager. The programmers are not so eager to pay for better tools. They do to some extent, but there's not a huge market, and that's the problem, I think.
Right, and so actually, so I'm wondering, so what do you think is easier, teaching people how to do performance engineering, or building good tools that will automate a lot of performance engineering work. So and the follow-up question would be, which way we should follow, as an industry.
Can you repeat the first part of your question?
Sure. Yeah. So what do you think is easier, teaching people how to do performance engineering work, or building a good tools that will automate building super optimizers, building some kind of recommendation systems, because actually, so one tool that I'm dreaming about is that having such sort of a recommendation system where for example, imagine you are writing let's say matrix multiplication code, right? And you are not an experienced, you're not a performance ninja, but you have this recommendation tool that sort of is already knowledge from other performance ninjas, and can recommend you the better version of the same code that will have the same semantic meaning, but that will be optimized for your particular platform. So do you think it's we can see something?
Okay. Yes, but what you're describing sounds a lot like an optimizing compiler, right? you take the code, you make semantic, you keep the semantic, and you produce other code that does exactly the same thing, but is more efficient. That sounds a lot like an optimizing compiler, right?
Well, maybe, yeah.
Because that's one of the key thing is that very often, right? The idea, a lot of optimization work has to do with changing the problem or changing the way you see the problem to approach it differently, right? For a typical thing that will improve performance might be to reorganize how you've laid out the data, for example, right? That can help, or stop copying the strings all the time, right? But these things very often imply that you change semantics. You change actually what you tell the computer to do. Because the compiler, I mean, if you're telling it, well, you must copy the string because later I might need the original copy, then the compiler might be stuck, right? It cannot know that you're never going to need the original copy. Or maybe you can figure it out, but if it's, I mean, obviously at some point, you compiler writers are super bright, but there's a limit to, how much work the compiler can do. So it's up to you to figure it out. I think my view of this is that the most fruitful thing would be to and maybe your idea is great, but my views would be to provide tools to help people understand better what's going on, because we need the abstraction, right? So we need to write JavaScript code sometimes, right? Because you need to write, a web application in the browser, it's probably going to be JavaScript for a certain reason, or it's going to contain some JavaScript. But the problem we have is that very often we're blind. We cannot see what's happening. And it's a little bit insane to how difficult it is to understand what's happening. Now, a programming language that's not super good at performance, but gets a few ideas right, is Go. So in Go, for example, first Go has this feature where benchmarking is basically part of the language, right? So if you type Go test, then it includes a benchmarking tool. It's built in. And then one of the things that it does is that by very easily, when you compile, you can add a flag, and it gives you, in a very readable fashion, all the inlining and bound checking decisions, right? Mm-hmm. So, and I'm not saying Go, because Go in the end doesn't end up being so fast, but at least, it gives you this kind of information. Now, other compilers do that too, but they often make it very, very, very difficult, right? So you can manage to get, Visual Studio will tell you whether it inlined this function or not, whether it waived this bound check or not, but you're going to have to work hard, really hard. You're going to have all this knowledge to know the right flag, to know all of that, or you're going to have to look at the assembly, and the assembly honestly is not very readable. I mean, it's painful to I can read like 20 lines, but at some point, like don't give me like 2,000 lines of assembly to read. I mean, it's painful. So yeah. So we need tools that to understand what's going on. That does the language that, if you've got an array access, okay, I want to be able to know whether there's a bound check there. Is there one? And I'd want to be able to, if I've got this piece of code, I'd like to see the assembly, but not the stupid
ugly assembly. I'd like to see something that
High level.
yeah, more readable. Not the stuff that something that's more like I can read assembly, but when I tell my students, okay, look at the assembly, what do you see? And they see, well, I see gibberish. And even if they took a class where they had to write assembly and so forth, it's like a foreign language. It's like, you're going to take one class of Spanish, and then I'm going to give you a Spanish novel, and I'll tell you, well, look at it. And you say, well, okay, it's all gibberish. Yeah, I took a class, but I don't do it every day, so I don't understand. So you really need to help people to understand. And as you know, like the assembly, like if you're not super experienced, the assembly can be misleading, right? Because if you got things are not as they appear. So there's a lot of nuances there. So you need better understanding of what's happening. And maybe the assembly idea is not good, but you could have your recommended idea is probably good, but I would do it slightly differently. So instead of recommending new code, I would probably try to inform the person. So here, for example, at this line, you're going to copy. Just going to be a copy of your large object. Are you aware of that? Because okay, so we have this project Roaring, it's a bitmap thing, and someone wrote and we have a C++ version, and someone wrote the 64-bit version of it, and in it, someone just last week figured out that during an iteration, we ended up calling. We ended up calling the copy constructor when iterating over a map, and it's something crazy that has to do with the fact that if you're passing an STD pair int, and yeah, if the type of the STD pair is not the one that's inside the map, then what the C++ does is that it copies the pair, and now it ends up calling the copy constructor. But it basically, even me as I'm fairly experienced in C++, but I did not catch that at all while reading the code. You really have to, you don't see it. It's not transparent, and that's really a big problem with because even if you teach a student, okay, try to write your code so that the compiler can avoid the bound check. Okay, but we make it hard even to find out whether that's happening. So how can the student figure out whether it works? We need to make it easier.
Right, that makes sense. So the 8th mage, you have something to add here?
Yeah, I wanted to say that I find that a lot of time assembly is unrolled in specifically the places where I want to see it, and like reading unrolled and interleaved assembly is really hard. And if I could have any tool that like de-interleaves the code into say a tree or an acyclic graph to look at it better, it would just make the reading so much easier. And like being a student and seeing those highly optimized unrolled and usually flattened inline functions, it really, I don't know how to do that.
I see. So one thing I actually wanted to add here is that compilers have those those things called optimization reports, right? So you can emit exactly actually what Daniel said. You can emit all the transformations that were made by the compiler. Let's say for example, this function was inline, this loop was unrolled, vectorized, interleaved, etc. Right? So that is usually more easier to understand than just parsing the assembly.
Right, but the compilers typically don't make it. I mean, basically, it's hard. I mean, it's there, right?
Yeah, it is still hard to understand sometimes. Yeah,
it's there, but it's not very approachable. So yeah, I mean, it will. So LLVM, for example, will give you this JSON dump or YAML dump or what happened, but then you're kind of like into Matrix, Well, even with the assembly thing, it reminds me of the Matrix, the movie where they're reading the symbols on the screen, right? And they see it real life because they're really experienced. They can see it's kind of the same thing, right? You have this gibberish, and you, if you're experienced enough, you start to see, oh, that's what's happening, right? But if you're not experienced, it's totally unapproachable. And yeah. I mean, all compilers will probably have all optimizing compilers have probably some way to tell you where they remove bound checks or where they're inline or something, right? But if you just for fun, you interviewed experienced programmers, and you ask them, okay, how do you get this information? You probably find that almost all of them don't know. They don't know how. I mean, yeah, if you're in the compiler team, then you know.
Sure. Yeah. Hey, Mark, you wanted to add something?
Yes, I was wondering. It seems like, I don't know if this is what you're looking for, but the creator of Cpp Insights, he when he wrote about why he wrote that tool, he specified the exact same frustration that you're talking about now, about not wanting to read assembly, but also not wanting to read the AST because it doesn't look very much like the programming language. So he wrote Cpp Insights because it actually shows you what the compiler is trying to do, but it looks very close to C++ for instruction purposes. So he actually used the example of showing students what their code is actually going to do, or what the compiler is going to do with their code, by looking at the output of Cpp Insights. So I'm just wondering if you looked at the output from that tool and that still was not what you were looking for?
Well, speaking for myself, I did not, but I should add that about everything I said, like basically, Dennis asked me whether we had good tools, or the tools that we needed, and I think at several places I said that I added the qualifier that either they're not there or they're not widespread, right? And right. So I don't know CPP Insight, but my impression is that this is not. It's probably not in widespread use, and so that's to me that's the relevant part, because even if all of the tools that they could dream of exist, if people, including myself, don't use them, then that's and why. Sometimes sometimes there are hard reasons for why the tools are not in widespread use. Sometimes there are commercial reasons, right? Just because nobody wants to make it nice and usable because they would want to be paid, and they don't have a business angle that works. Or sometimes it can be a problem of culture. So for example, I was trying to point out at Go. Now, Go integrated benchmarking in the language is part of it. So that was a very, very good decision. Now, if you're in Java, for example, and you want to write a benchmark, then you've got something like GMH, which is good, but you have to learn to use it, and it's not part of the language, right? So so it's not sometimes that the tools are not there. It's that they take extra effort to acquire, to install, and so forth. And I really think that we need to not only build the tools, but also spread them around and make them more popular.
Yeah, that makes sense. Yeah. So actually, so anyone else here in this room have and essentially, like, if somebody here, like, is an outsider, let's say from the performance engineering community, and wants to speak about the quality of our tools, what experience do you guys have?
Well, I say that I'm not a performance engineer. I'm implementer of research code in my company, and I can say that I have very good experience using the Xcode performance analyzer. And when you talk about not just CPU but GPU or something like even further than that, then you mostly don't have anything. Like it's very buggy, it's very slow, and it's very hard to use.
Okay.
Yeah. I mean that's so even when you have good tools in very simple context where you have a very well defined context, the minute that you're trying to use fancier stuff on the edge, then you're often in big trouble. But it also goes to the documentation and everything. The more on the edge you are, you quickly end up even running out of knowledge. I mean, if you don't know people, then it's very, very hard. So it's probably not a problem that's going to get solved tomorrow, because the problem is that as we're evolving, we're working on harder and harder problems that are far more complex. For example, when debuggers were started, something like 40 or 50 years ago, code was single-threaded. There's no such thing as multi-threaded code. That was ridiculous. So you had these debuggers, work okay, but then at some point we got this crazy code that has different threads, and then then you have GPUs and everything. Then it all falls apart again, and so you have to reinvent new tools. And I think we go back to this idea of coevolution, right? So all of the parts are changing, and everyone needs to adapt. And I think software performance is, unfortunately, like the tooling. It's not that it's not there. It's just like the practices and the culture is about 20 years behind, or even worse, what other aspects of software development are. So things like testing are far more sophisticated and far more advanced and far more culturally validated than software performance. Software performance is pretty much on the edge, or the bleeding edge, where there's really few resources.
All right. Yeah, that's interesting. So Daniel, actually, let me ask you this. So what are the most frequent performance traps that you see developers are making?
Well, I mean, I think we covered this, but I think that the first one is that they're just not benchmarking in the first place,
Right.
which is not the answer you want, but that's really a true answer. One of the major, an important one is an architecture issues. Is that sometimes they don't think enough about how their data is laid out, and how is the data going to come from, and so forth. So we stressed for many years that the way to build, at least on campus, we told students to do UML diagram, where you organize your classes and so forth. But I think much more importantly, you should think about your data flow, right? Where is your data, how it's going to move, and so forth. And if you get your data structure right, basically, and if you know how the data is going to be laid out, and if you do it in an efficient manner, then it's fairly easy afterward to even if your code is inefficient, it's easy then to optimize it. But if you get the basic organization of your data wrong, then it's really crippling afterward. So a few years ago, I was doing consulting for a company that had built this system. Was basically stuck in hell, and the reason they were stuck in hell is that they were basically relying very heavily on hash tables. So everything was hash table, and they had giant hash tables, and so basically every single step in the application involved random access, and they had lots of data, and so they were constantly hitting cage misses. And their developers were quite good. I mean, they had really bright guys who were working hard, but they were working from this architecture that was doomed. I mean, there was just no way to salvage it because basically, at the core, they did not have locality. They did not. When I work with students, because I've got less experience reviewing code. When I work with students, one of the problems I see very often is the problems that have to do with the lack of knowledge of how the hardware works. So even students who went through college, took a system architecture class, and so forth, they very often they're not because they're stupid, but because they lack experience. They don't understand. They don't understand how the machine works really, and so for example, they'll assume that adding a lot of if clauses to avoid work it always pays, right? And so they tend to write very branchy code. One trend, and that has to do with my age, I guess. One trend that I don't like all that much is the push toward functional programming. Now, functional programming by itself is fine. I've got the Haskell book and so forth, and I've got nothing against it per se. But very often people replace simple loops that they can understand with function composition and so forth. And then the problem then is that it gets really hard to understand what's happening at the level of the machine. And so sometimes it works. Sometimes, you're going to get the abstraction for free, but sometimes it's going to be terrible. And if you're not benchmarking the alternative, and you probably aren't, then you don't know that it's terrible. In the example with the roaring bitmaps that I was giving earlier, This was actually the result of using functional programming. So I think functional programming is really a mixed blessing as far as performance goes. That's one angle. Another thing that I see with students very often is really a focus on object-oriented programming, which is probably has to do with how they teach the students. And the problem with that is that they're basically abstracting out. So they want to have lots of little objects. And then if you look at the data is organized when you do it that way, then you get a very fragmented data structure with lots of random access all over the place. And that's a terrible design. So you want to avoid such designs. And so unfortunately you get into you get into this strange thing where you have to get the students to learn some patterns that were recently thought. But that's not uncommon. Actually, it's a problem that's generic with programming. A lot of things that I think students learn in college, they have to unlearn. Like, for example, they have to unlearn that before, when they start a project, they have to draw the UML diagram of the entire project. That's probably not something you want to do. Same thing when you design a database system, you're supposed to do the conceptual design and logical design and physical design, and the physical design is supposed to be last. And so basically, this is almost a guaranteed recipe to produce trouble and actually low performance, because the whole idea is that you say, well, the physical design is irrelevant. So I think I would when I teach my students, I try to get them to flip things around. Think first about physical design. How are you going to lay out your data before you start programming? And don't program and then figure out later how the data is going to be organized. That's a critical mistake, I think.
Yeah, cool. That's a great answer. So Daniel, any book recommendations, any study recommendations, any other materials? Like, please share what where you are, getting new information. Any particular podcasts, whatever. And actually, it's not strictly related to performance. Like, and it can be anything.
Right. So I think your book, it would be a recommendation, just because not because it's you, but even if you were not present, I would probably want to recommend your book, just because even if someone does not like the book, there's not a lot of competition, so it's an easy recommendation to make. So performance analysis and tuning on modern CPUs. I think you probably want to get that book, of course. And I think we already mentioned Hacker's Delight by Warren, which is a classic, and it's not super readable. It's much less readable than your book. Some of it is a little bit crazy and hard to follow. There are crazy math proofs that go on for pages and pages. But it's a really good reference, and it's actually worth getting in paper form, because you're going to get the PDF, but it's hard book to play around with in PDF. We talked about youth, and I think again, his book is really thick and very, very, very expensive, but it's actually worth having, because if you ever have to do really, really insane things like optimize circuits or and so forth, it's all there. Sometimes it's really, really hard to read. But then on the other hand, if you can find the right reference there, and then you can cite news, then you'll feel really good about citing the authority, and people will stop arguing with you because then you got the ultimate reference right there. There's a great Twitter community, so I don't want to list everyone. There's the possibility to have list on Twitter. So probably someone has made a list of, maybe you have, there's probably someone has made a list of people who are relevant to performance computing. So that's really, really important. But anyhow, even if you just like follow you, for example, or follow me, then people can find out from there and go all sorts of directions. Obviously, well, everyone, people are here that you probably know about Hacker News. That I don't read Hacker News, but I think it's a reasonable, and I don't tend to participate in posting board and so forth because I want to have a life and a family and so forth. So I don't want to be arguing with people about stuff. So avoid that. But it's fine. There are a few blogs, like you mentioned yours. There's mine. There's a few more. I haven't prepared a list, but and these things, unfortunately, they tend to come and go. So people are not really good at posting all the time. So I've been posting since since 2004. So my blog so my blog is a long continuous stream. But unfortunately, some people, they start and they stop, so they're harder to recommend. And as I was saying, they're pretty decent. They're pretty decent conferences, and a lot of them last year were free, in the sense that you could attend by Zoom. So this was a great opportunity. Unfortunately, what happens at some conferences is that the performance stuff or the low-level stuff is a little bit on the side because maybe it attracts fewer people. But then on the plus side, then you get to meet, you have more time to meet because it's less crowded. So that's great. And I do think we should probably, we could do more to organize. So for example, I was suggesting we do competition, and yeah, and we should do list and but basically what you're organizing there is really a great thing too. Like this, I don't know if you're going to keep with it, but Twitter Spaces and other venues like that can really, really help, I think. There are podcasts, but I don't know how much of these podcasts are. So there are relatively few, in my experience. There are relatively few high quality programming podcasts, and I don't. Maybe there are some, but I don't. I don't know of any that are ongoing and really active, that really there was Cliff Click who had a podcast at some point, but I think it's gone, or he's no longer doing it. It was really great, but I think it's probably gone.
Yeah, he's now organizing those compiler coffee clubs.
Okay,
so happening on Friday morning Pacific time.
Okay, so you moved on to something else. So yeah, maybe I saw about that. But that's unfortunate because his podcast was absolutely fantastic. But then he's got this style where he talks really, really fast, and he's really energetic and so forth. So that was really a lot of fun. Yeah. And of course, a lot of great discussions about performance happen on GitHub, right? Or sites like GitHub, where you follow through, especially like the some of the big projects when they have performance problems. It's really worth going there, and can be in any programming language, but very often the exchanges are very interesting, and people there's lots of smart people. But yeah, I would say, coming back to something I said earlier, it's really about listening to the people, and it's really more about the people than the books. Like, like your book is great, but it's probably more important to be in touch with you than just having the book and not being in touch with you. So yeah,
that's great. So Daniel, anything not related to performance? So one podcast actually. So I'm constantly listening to is Lex Friedman's podcast. So he's bringing like amazing guests there, and
yes.
And it's just great, overall education, like keeping track with with new ideas.
Oh yeah, I mean, I'm a really big fan of podcasts, and maybe after this chat, I could list the podcast that I'm subscribed to. But I was more thinking in terms of like software performance, right?
Right.
And I'm subscribed to his podcast and a few others, but I was trying to think in my head about stuff about software performance. But yeah, and basically because. But an important point that's worth making, and I tried to make it, is that software performance is part of. Basically, if you believe that things can be made more and more efficient, then you're probably a little bit of a techno-optimist, which means that you think that technology is on the slope where it always gets better. And if you are, then you should be interested in a lot of different related fields where you see people, whether it is in physics or material engineering or economics. You should be interested in how these fields progress, because basically it's all socially it's all very closely related, right? The way, for example, they're making solar panels that are much more efficient than they were like 5 years ago. It's not entirely different as a process from the way we make software run, using much less energy today than we were 10 years ago. It's basically the same kind of at the high level, it's the same kind of effect. So we're all doing more or less the same work at some level.
Yeah, that's great. So Daniel, what are you now working on? Do you have anything you can tease now? Any new projects? Any new SIMD-JSON like breakthrough?
Yeah. Okay. So okay. That's a good question. Okay. So SIMD-JSON is not so it's our really fast JSON parser. It's not done yet, so we're still actively working on it, and we have we have a few key ideas that are still not very well published and well documented. So one of the things we're working on in SIMD-JSON is something called the on-demand front end. So it's a way to consume JSON, which I think, even if you don't care about SIMD-JSON, is a great way if you care about performance. So it's kind of a way to stream through it, but while we're giving you the illusion that you've got a a pre-parsed document, but you're really just streaming through. So that's really a neat thing, and it's becoming our default, and we're pushing that. We're hoping later this summer to publish version 1.0 of SIMD-JSON with even better documentation and so forth. And we're hoping other parsers may adapt the same front end, because we think it's a step forward. Yeah, so you mentioned fast load. So the way we found that a faster way to parse numbers. So it's not default in Go, and it seems that a few people are organizing themselves to push it in Rust, so that it becomes the default. And there's also a very high quality port in C#, and there are discussions to push that to the runtime as well. As far as like more secret projects that nobody has seen before, well, so we're continuing work on. So there's a data structure called the Bloom filter that sometimes people use for performance. It's a way to do set containment filtering. We last year or the year before we published we proposed something called the Xor filter, which is an approach that is can be more concise, smaller memory usage, and faster. And we're working on a follow-up that's going to be even better. So it should come out this summer. We're working hard. It's still a secret, but it's going to be a big thing. I think it's going to be a big step forward. I've also got so I was working on Unicode validation. Now we have another project that has to do with Unicode that should, again, a little bit secret, but it should come out this summer. And it's again, it should be a little bit, I think it's a little bit impressive. So we're going to promote that. So yeah, I've got a couple of really nice, or maybe 3 or 4 nice things coming this summer. So people should, follow me on Twitter or GitHub and my blog, of course, and then I'll be announcing these new developments soon. And then I've got a long list after that, but
well,
then
that's great.
But that's the thing, right? In our field, it never ends because there's always much more to do.
That's true, and everything will be open source, right, on your GitHub.
Yeah, eventually everything is. So what I do is I try to produce high quality, production ready software, but often. Sometimes I talk about secrets, but secrets are not commercial secrets. The reason why some projects are secret is because so there's an interesting psychological effect where you if you drop something publicly, then there's a risk that there might be noise. People come in and then you waste time because the project is not ready yet for observers, and then they have questions, but then they drag you down because you're not ready to answer yet, and then there's also a psychological effect on the people working on the project. It's really, I find that if you're working on something and it's not ready to show the world yet, it's really better to keep it more of a secret. It helps you focus a bit more, and you're more motivated to work on it. If it's out in the open and it's ugly, I find that there's a psychological issue with it. So if you think, for example, if you're repairing a car that you want to show the world later, it's better to put it in your garage and close the door, not show it to anyone, and then you go work in the afternoon on it, and then you show it to the world already, rather than having this ugly car on your lawn every day that everyone can see. That's more. I think it's more psychologically depressing. so I prefer to have some projects that are like secrets because they're not ready to show yet. Right.
I'm 100% agree with that. Yeah. Well, I guess. So we should wrap up probably, right? We're already talking over 2 hours. So well, Daniel, it's been great talking to you today. So again, I would like to thank you for all the work you're doing. So for all your open source projects, for all your blog articles, I actually like all those small, really focused posts that you're writing. So that's great. And yes, so sure, Daniel, I would love to see you next time, right? Joining us.
Yeah.
And unless anybody has any final thoughts, comments, or remarks, or whatever, we'll see you in 2 weeks. All right, then probably I will end this meeting. Thanks, everyone. Happy performance tuning. Bye.
Bye-bye.